section. At first, it's going to seem really hard, but I promise you, this is going to be so easy because all of this stuff is the same thing that we did in the last section. There's just like a very slight difference and something a little different we do with the critical values. Okay. Miranda already sees it. Okay. All right, but before we talk about that, I do want to talk about a new distribution, okay? We talked about some distributions before. We know the binomial distribution. We know the normal distribution. There's a new distribution that isn't really used that much, but we do use it in this section. It's called the T distribution, okay? Some things about the T distribution, it was created by this guy who worked for the beer company Guinness, which I think is kind of cool. And it also depends. So it's not just like one graph, like the normal distribution. I mean, it is one graph. It depends on the mean and standard deviation. The T distribution depends on this thing called the degrees of freedom, okay? And basically what it is, well, we know that N is the sample size, right? The degrees of freedom is going to be the easiest formula you'll ever know in this class. It's N minus 1. Okay, it's going to be the easiest formula. You barely even have to memorize it, right? You just take the sample size and subtract 1. Okay, now if we zone in on this graph here, I have a bunch of different T distributions plotted, okay? Now, the solid black distribution here, this one is actually the bell curve. This is the normal distribution, okay? But then all these other distributions are the T distribution. Now, if we focus on this like beige one, on like the shortest one here, this is the T distribution with 1 degree of freedom. So, I mean, it's a little shorter than the normal distribution. It's almost like I took the bell curve and I like pushed it down. So it's a little bit more like squat. So it's a little wider, a little bit shorter. This is 1 degree of freedom. Now, if we jump up to 4 degrees of freedom, now we're at this blue graph here, okay? Now, this blue graph is a little bit taller and a little bit more narrow than 1 degree of freedom, right? And as we go on to 10 degrees of freedom, now we're a little bit even more taller. And actually, as we increase the degrees of freedom, the graph looks more and more and more like the bell curve, okay? If we had like 1,000 degrees of freedom, it basically would be the bell curve, okay? Just for those smaller degrees of freedom, the graph just looks a little bit shorter and a little bit wider. All right, let me... All right, so that's the T distribution. Some things about it, I just wrote some properties. I don't even know why I wrote this. It's symmetric, it's unimodal, just has 1 peak. It's more spread out than the standard normal distribution. And as we increase the degrees of freedom, it looks more like the normal distribution. Okay, that's literally all you have to know about the T distribution. We're done talking about it. Okay, section 8.1. This describes stuff that we've already done before. So the last section, the last packet of notes that we've done, I think it's just good to kind of recap what we did here, because if you put them side by side, you'll see how similar the next section is to the last section. Okay, so in this section, we're given a bunch of different symbols, okay? The questions will give us a bunch of different things. For example, it'll tell us what the population standard deviation is. Okay, anyone remember the formula for population standard deviation, or the symbol? Michael?
Sigma X bar.
Oh, okay, so you're like, okay, that's sigma X bar is like the standard deviation of the means, but sigma itself is the population standard deviation. Got a little too specific for me there, but that's good. You're also going to be given the sample mean. Okay, sample mean. Okay, anyone know this symbol? X with a line over it, or X bar, right? Then we know the sample size, which is N, okay? And then we're also given a percentage, okay, which is also called the confidence level. It just tells us like how confident do we want to be that our mean gets in that interval, right? Basically, questions will only give us these 4 pieces of information, and the overarching question in this section is for us to figure out what mu is, right? We don't know what mu is. We want to figure out what it is. Now, these 4 numbers are not very helpful to find the mean. Like, we literally can't calculate what the mean is based on the information that we have. But what we can do is we can come up with an interval that we're pretty confident that mu is in, right? So how we did this, first we had to find the critical values. And I don't know if you remember, but we used the chart to do that, right? So we just took a look at the chart, we found the critical value. I don't know if I specified this, but the chart actually relied on the normal distribution. Okay, so the bell curve actually had to do with the chart. All right. So what I want you to do is I just want you to put an arrow to this chart here and just say the small chart. And I can't spell for some reason, small chart. Okay. And if you're wondering why it's small, well, you'll see the big chart later. Okay. So critical values, use the chart. Standard error, does anyone remember the formula for that one? Give you a hint, it's a fraction. Give you another hint, there's a square root in it. Nathan?
The standard deviation
Perfect. Over the size or the,
yes.
yeah. So standard deviation over the square root of n. It was a formula you had to memorize, but I mean, you already memorized it when you learned about the central limit theorem, so it's really not that bad once we're here. Finally, to get the margin of error, we just multiplied the two numbers we found, right? So you took the standard error and you took the critical value and you just multiplied them together, okay? After you find the margin of error, it's pretty easy to get your interval because you just add and subtract it to the estimate. You write it in interval notation. You write your answer in words using the template. And that's kind of how the last section went, right? Now, this section is going to be a little bit different, okay? But it's going to be very similar as well, okay? In this new section, we're going to be given problems that tell us a bunch of information. We're going to be given the confidence level, okay? We're going to be given the sample size. We're also going to be given the sample mean, okay? The only difference between questions in this section and questions in the last section is, well, instead of the population standard deviation, we're given S, or the sample standard deviation. Okay? It's the only difference between the last problem and this one, okay? We're still trying to find out what the population mean is. And if you think about it, questions in this section seem more realistic, right? If you're doing an experiment, of course you know the sample size. You can calculate the sample mean because you have your data points. And it just would make sense. Like if you know how to find the sample mean, you would also know how to find the sample standard deviation, right? So most situations are like this one. It's kind of weird to know the sample mean and somehow know the population standard deviation, but not know the population mean. It's just kind of weird in the last section. Like, how would you even know this? So this section is way more realistic than the last one. Okay, so the only difference is that we're given the sample standard deviation in this section, okay? And actually the steps are pretty similar, okay? We're still gonna find the critical values and we're still gonna use a chart to find the critical values, except we're gonna use a different distribution to get to those values. In the last section, we used the normal distribution. Anyone wanna guess what the distribution is this time? T, right? There's a reason why I talked about the T distribution in the beginning, right? The T distribution plays a part in finding the critical values, and it actually creates this chart that we have to use, okay? Now, point to the chart, okay? We're gonna use the big chart. And if you're wondering what the big chart is, well, if you go all the way to the back page of your notes, ooh, we have the big chart, okay? And you're probably wondering, like, oh my God, what is this big chart here? I promise you it's not that bad. It looks intimidating, but it's really easy to find values in this big chart. We'll get there. It's not as bad as it looks. I promise you it's not that bad. Okay. All right, let's keep going. Let's say after we find the critical values using the big chart, we have to find the standard error, okay? And here's the formula for the standard error. It's S over the square root of n. Okay. Now you're like, oh man, I have to memorize a new formula for standard error now. You don't have to memorize it. Okay. This is still the standard deviation over the square root of n. It's just using a different symbol because now we don't have sigma, right? So you don't have to memorize a new formula for this. All you need to know for standard error is it's the standard deviation, either S or sigma, over the square root of n. Okay, so no new formula here. It's just a different symbol. Okay, finally, margin of error, same thing, SE times CV. If you want to find your interval, same process. You want to interpret your results, same process. Everything's the same in this question, except now you have S, right? You're using the big chart and you're have like a really similar but like slightly different formula for the standard deviation. So everything's pretty much the same. Okay, I guess the big question is how do we use the big chart, right? That's the biggest question. I promise you it's not that bad, okay? So let's just say we want to find the critical value for this section where we're using the big chart, okay? The first thing I want to notice is sometimes instead of critical value, the textbook will use some weird symbol. It looks like this. It's a T with like alpha over 2, like on the subscript, okay? Don't worry when you see this on the homework. It's literally just telling you to use the big chart to find the critical value, okay? It's basically like some people like to have a formula for some of these things, and T alpha over 2 just tells you to use the chart, but I just think it's easier to call it a critical value. So if you see that on your homework, just do this process. Okay. The first thing you're going to do is find the degrees of freedom. Does anyone remember the simple formula for that? N minus 1, right? It's the easiest formula you're ever going to have to know in this class. Just take the sample size and subtract 1. Okay, now if we go to the chart, okay, if you notice that on the chart on the left, we have degrees of freedom, right? And each of the rows are labeled on how many degrees of freedom we have. So if you have 14 degrees of freedom, you're going to use the row labeled 14, okay? So figuring out what row you're going to use is pretty easy. You just have the labels based on the degrees of freedom. The harder part is to figure out, okay, what column am I using? And if you take a look at the labels on the top, they're kind of confusing, right? They have all these weird numbers, and it represents like the area in the right tail, which I honestly I used to teach this, but I found an easier way to do this. So what we're going to do is we're actually going to cheat, okay? And where we're going to cheat is if you go to the very back page of the chart, the columns are labeled based on confidence level, okay? I don't know why the textbook does this. I think they kind of want you to be confused at first because they want you to do it the other way and get those numbers up top. But what we're going to do is, well, when I give you the test, I'm going to give you this chart. What you're going to do is you're going to cross out the labels on the top, okay? So you don't have to look at those funky numbers, and you're going to relabel them with the numbers at the bottom, right? I think that's the easiest way to go about this, okay? So basically, the first column is going to be your 20% column. The second one, 50, 80, 90, 95, 98, 99, 99.5, 99.8, 99.9. Okay. And honestly, I think this is just the easier way to go about it for now, just because, well, we haven't really learned how to do that much with the area and the right tails anyway. And it's literally given to us on the chart. Might as well use what we have, right? Okay. Now, if the chart didn't have it at the bottom, then we'd have to actually do this, but we're not. We're just gonna use what the chart gives us. Okay, so the row is the degree of freedom, and the column is the confidence level. Let's do an example. Okay, we have a simple random sample of size 10, so n equals 10, right? Drawn from a normal population, 95% confidence interval. For some reason, I literally have to write it down. If I don't write it down, I will not get it correct. Okay, so the first thing you have to do is find the degrees of freedom. This is something a lot of people forget. Some people just like go to row 10, which is not what we're going to do. How do I get the degrees of freedom? N minus 1. And this time it's 10 minus 1 because n is 10. So the degrees of freedom is 9. So on your chart, you're going to look at row 9, okay? And the 95% is going to tell you what column to use, okay? So let's just go to the chart. Okay, on my chart, I have row number 9. I have column for 95, and where they intersect, 2.622, oh my gosh, 2.262 is your critical value. So I promise you the big chart is not that bad. It's kind of like the old chart, but you just have that degrees of freedom going on as well, okay? Okay, so we all agree that the critical value is 2.262, right? Okay. Well, I think you know what's going on. I cannot write 2.262. There we go. Why don't I give you like 30 seconds to work on example number 2, try to find out using the chart what your critical value is. All right, so here we have a sample of size 15. We want to do a 98% confidence interval. How many degrees of freedom do I have? 14, good. So that's the row we're going to use, right? The column corresponds with 98%. Do we all agree that the critical value is 2.624? Cool, right? So just looking at the chart, not too bad. Now, there's one thing that does make the chart confusing, okay? If you take a look at our chart, on the first page, there's actually a degree of freedom for every number that we have, right? 0 or 1 through 30, right? But then, well, once we get to the next page, we're good until 40. Once we reach 40, oh, now we're going to 50. And now we jump all the way to 60. And then like once we reach 60, now we're jumping 20 over to 80. And then like there's no numbers between 100 and 200, right? So what if our degree of freedom is like 170, right? You don't have a row for that. And then it kind of seems like you can't use the chart, okay? Here's where convention kind of comes in, okay? There's really no reason for why we do this. It's just like how mathematicians agree to do this. If you don't see your number on the chart, you basically round down to the lower number, to the next lower number on the chart, okay? So for example, if your degrees of freedom was, I don't know, 98, you would round down and use row 80, okay? So you're probably wondering like, okay, why don't we round up or down? It's literally just convention. Remember like when we did percentiles and quartiles, like it was just convention that we rounded down. It's the same thing here. We just go down. All right. So let's do an example. Example number 3 says we have a simple random sample of size 58, so n is 58, drawn from a normal population. We have a 99% confidence interval. So first, let's find our degrees of freedom. How many degrees of freedom do I have? 57, perfect. Now, there's actually no row on the chart that says 57. So we have to look at our chart and see, okay, what's the next lower number on the chart that's not 57? And which one is it? I think there's one higher than that. There's a 50, right? So I think 50 would be the next lower number on the chart. So I'm going to use row number 50, okay? And the column for 99, okay? And let's see what happens here. All right, row number 50, column, what did I say, 99? Here we go. Are we getting 2.678? Cool. And that becomes our critical value. All right, so CV, equals 2.678. Now, the last question I get about this chart is, once we reach 200, there's nothing after 200, okay? So for example, if you have 400 degrees of freedom, you're probably wondering what to do. In that situation, well, I'll tell you, I'm actually never going to give you a situation like that, so you don't have to worry about that. Well, basically what you do is once you reach 200 or go past it, you're going to use this part of the chart. And I don't know if you remember, or if it looks familiar to you, but the small chart is actually this chart, okay? So basically what happens is after we reach 200, the t distribution looks so much like the normal distribution that, well, you basically get back to the small chart, okay? But we're not going to do that because I feel like that's just too many caveats here. How about this? Why don't you try example number 4? I'll give you like 30 seconds to work on that one, and then we'll come back. I think I see everyone kind of finishing up here. N is 92 here, right? All right, we want to do a 50% confidence interval. Do we all agree that we have 91 degrees of freedom? Yes. Can we all agree that we're using, oh gosh, row 80? Cool, because that's the lower one on the chart, right? We're using column 50%. Oh, did not mean to erase that, right? Do we all agree that the critical value was 0.678? Yes, all right. So does anyone have any questions about using the big chart or anything like that? Is it a little bit less intimidating now? Okay, I promise you it wasn't that bad. It just looks really scary at first. And then once you know how to use it, it's like, oh, well, it's just the big chart. It's not that bad. All right, let's piece everything together. So I didn't really talk about assumptions yet. So we do have some assumptions for these questions. First of all, these questions don't give us sigma, right? So the whole point of that first question was basically when we put everything together in this whole chapter, we're going to ask ourselves, okay, is S given or is sigma given? And that's going to tell us which chart to use, right? In the last section, we used the small chart. This section, we're using the big chart. In this type question, I'm going to ask you if S is given to us. Are we given the sample standard deviation? Okay. The second assumption is still the central limit theorem. Now, the central limit still does kind of play a part in here. It's kind of hard to explain like where, because now we're dealing with the t distribution, but it's basically the same thing. So we still have to ask ourselves if either the sample size is large enough, so bigger than 30, or if the population is somewhat approximately normal. Okay, so the same assumption that we did for the last section. That's step one, okay? Now, step two, I used to teach in my class, but I realized that it took up so much time that it just wasn't worth it. So what we're gonna do is we're actually gonna scratch out step two, okay? If you weren't given the sample mean and the sample standard deviation and you were just given a list of numbers, you would have to do that. But it just takes so much time to do that in this class that we're not even gonna go there, okay? Step three, we want to find the degrees of freedom and use the big chart to find the critical value, what we did on the last page. Step four is computing the standard error, which does have this formula, which is different. But remember, it's the same thing. You're taking the standard deviation over the square root of n. It's the same formula. You don't have to memorize this. It's just the same thing you were doing before. Step five, the margin of error by CV times SE, same thing we did. Step six is the same thing we did in the last section. Step seven is the same thing we did in the last section. So basically, once we get that margin of error, or the standard error at least, everything else is the same. Okay, let's put this all together using an example. All right. So example one, we have a food chemist. Interesting job. Sounds kind of fun, except that the food isn't good. But a food chemist analyzes the calorie content of some sort of chocolate cookie that's popular out there. I guess they can't say the brand name in the textbook because that would be, I don't know, maybe something bad. But to do this, we took a sample of 8 cookies. Now, I'm actually going to go through and write down all my information below the question as I'm reading through it. I think it's a good practice to do that just because if you start doing the question without writing it down, then you start getting confused as to like what numbers go for which spots, okay? So it looks like the sample had a mean of 115.375. Now, I think it's pretty obvious in the question that this is the sample mean, right? Because it's in the sentence, the sample had a mean. So I'm going to say this is X bar, 115.375, okay? And then it says, and a standard deviation of 2.825 calories. Okay, well, this one's not, oh, you're good.
Sorry,
This one's, no, you're okay. You missed out on the party.
thank you so much.
Okay, so once we get to 2.825, it's not telling us that this is the sample or population standard deviation. Any ideas on which one this is, sample or population? I think it's S, right? I think the big hint here is, well, first of all, in this section, it's always going to be S. But once we start mixing it all together, whenever it's in the same sentence as talking about the sample, even if it doesn't explicitly say that this is the sample standard deviation, it's kind of obvious that it's clumped together with the sample, right? So this has to be S. Okay, S equals 2.825. And I know it seems obvious right now, but I promise you when I start clumping it all together, it's going to be confusing which one's the sample and which one's the population. Okay, it is known from previous studies. Ooh, that's our textbook's way of telling us, oh, we're talking about the population now, right? And then it says the population is approximately normal, okay? And we want to do a 98% confidence interval. So I'm going to write that down as well. Okay, so now all my numbers are written down. I actually don't need to go back to the question to figure out, okay, what goes in which spot. So we're doing good, okay? Okay, assumption time. We need to ask if S is given to us, right? Well, S is given to us. It's 2.825. So S is given. Okay. The reason I ask this is because later on, we're going to have to figure out, okay, is sigma given? Is S given? It's just good practice to be like, okay, S is given. I can use the big chart. We're good. Is the sample size bigger than 30? Well, the sample size is 8. Is 8 bigger than 30? No, right? So that's a sad face. Does that mean we can't do the question? No, actually, the big hint here is usually like, unless I don't ask you to do the rest of the question, if I'm asking you to calculate the critical value and the standard error, the answer is going to be yes, right? Because I don't want you to do it without having to do it, right? Okay. Is there anything about a normal population here? Yeah, right. It's literally up here. The population is approximately normal. So I'll just write population normal. Okay, it's mentioned, which means we get a smiley face, which means we can do the question, even though we have a small sample size. All right, part B is using the big chart to find the critical value. I think the biggest mistake I see people do here is not finding the degrees of freedom first, right? Let's find degrees of freedom. What's the simple formula for that? N minus 1. So since n here is 8 and I subtract 1 to get 7, 7 is the row we use on the big chart. Okay, so let's just go ahead and take a look at the big chart. Okay, I know I'm using row 7 and the column using our little cheat codes here. Since we have a 98% interval, it's 2.998 and that's it. All right, so that is our critical value. CV equals 2.998. Okay. All right, let's keep going. We need to find the standard error. Does anyone remember the formula for standard error in this section?
S over square root of.
Perfect. S over the square root of n. Now, it's not a new formula to memorize though, right? It's the same formula, except now we're using S instead of sigma. It's a good thing that I wrote down all my information up top here because now I don't have to dig through the question to figure out what S is and what N is, right? All I have to do is look at my stuff, plug in my numbers. I know that S is 2.825. I know that N is 8. Once I'm here, I personally like to do the square root, write it down, and then divide, unless you have a nice fancy calculator that can do it all at once. Because if I don't do this, then I kind of mess up. The square root of 8 is 2.828. And then when I divide this together, you should get something along the lines of 0.999. Okay. Next up, we have to find the margin of error. Does anyone remember the formula for that one? Perfect, CV times SE. So you just take the two numbers that you found, multiply them together. I know my critical value was 2.998. I know my standard error was 0.999. So when we multiply these together, we get 2.995. The margin of error is the thing that like really makes the interval, right? It's what defines the interval, defines how big it is. So now we're ready to create our interval, okay? We start by, well, we have to figure out where approximately the interval is going to be, right? Since we're trying to find the population mean, we're always trying to find that, right? Where the interval goes is the best approximation for what we want. The best approximation for the population mean is the sample mean. I didn't mean to erase that. Here we go. Okay. Now the sample doesn't exactly mimic the population, but I mean, if the sample means 115, then I would assume the population is somewhere around there. So that's going to be kind of the midpoint of my interval, 1.5, 0.375. To get the higher and lower numbers, you're just going to add and subtract the margin of error to your point estimate. So I'm getting 118.37 on the right. When I subtract, let's see, minus 2.995, I'm getting 112.38 on the left, okay? And then when you write your interval, there's a couple ways you can do it. I think the easiest way, which I never really ask, is to do the plus or minus notation where we write how we got to it. So I took my middle number, I added and subtracted 2.995. Okay, so that's one way you can go about it. You can write it in interval notation where you write the smaller number on the left, the larger number on the right. Okay, and the last one that I always forget to take out of my notes when I write this up, but I haven't taken it out like year after year, is using like less than sign notation. So 112.38 is less than mu, which is less than 118.37. Okay, so 3 ways you can write your answer. I think like interval notation is probably like the most useful, but either way is fine for me, unless I specifically ask you to do it. Finally, interpreting your interval in words. You're literally using the same phrasing as the last section. So you don't have to memorize anything different. It's we are, in this case, 98% confident okay, that what we want, mu, is between the two numbers we found, 112.38 and 118.37. Okay, it's very important that you use the template or at least kind of like know what you're trying to say when you do this. Statistics is kind of like an English class, right? If you don't say it in the right way or the right phrasing, you risk communicating the wrong thing and then you get marked wrong for it. So I would just memorize the template and use that to write out your answer. All right, any questions on this example? Alrighty, then I honestly don't think we have enough time to do the next one because we have a quiz review to do. So how about this? We're gonna end here.